Hello and welcome back to Precalculus. We are talking about trigonometric equations today. And as any other equation, before your goal is to calculate the unknown quantity. So what you are used to, right, your previous life, x plus 3 is equal to 6. Let's go 8. And then you subtract 3 on both sides, and you have your x equals 5. Now, to solve this problem graphically, which you can graph the two functions you have, one on the left and one on the right. Since I don't need the negative numbers, I need positive, I make this look weird, but that's okay. And we have on the left side, we have x plus 3, 1, 2, 3. So that's going to be a 45-degree line going forever up and down. And then 4, 5, 6, 7, 8. So this is equation y equals 8. This is equation y equals x plus 3. And what you see here is that these two equations intersect at this point, and that point is 5, 8. So that point has x equals to 5. So that's the solution. X equals 5 is a solution because that's where the left and right equations intersect. Now, you might ask, why are we talking about ridiculously easy algebra problem? And in the weird way, because you are not used to solving equations graphically. We talk about it because this will greatly help your trigonometric equations. You see, when we solve algebraic equation, we know that x is equal to 5 and we're done. But for trigonometric equations, you might have 2 solutions, 4 solutions, 16 solutions, infinitely many solutions, because it will depend on the domain that is given to you with the equation. So if the trig equation is given on the entire domain, your solution is going to have infinitely many values in it, and we have to show them all. Now, there is a specific way you show them all. You don't sit there for eternity plugging in numbers. But the thing is that you have to be able to see and represent those solutions. Now, another thing is as simple as, sine x equals 1/2, right? You, in your head, because of what you had before, you're thinking, oh, sine of 1/2, so, well, that's easy. It's just 30 degrees, right? Because you memorized from the chart, right, that sine of 30 gives 1/2. And I say, yes, correct, but it's incomplete. So, if you answer that on your test and you just write, 30 degrees or pi over 6, which is better, then you might not get even a half a credit. Now, you might ask why. Why is that so? Because the answer is correct. The answer is correct, but it's incomplete, as I said. Now, why would that be so? Well, in this class, right, in chapter 4, we learned to graph the basic sine function on 0 to 2 pi, which is that principal period we talked about, right? It goes all the way up to 1, goes all the way down to -1, and in this case, right, we just have this principal period 0 to 2 pi. If I draw the right-hand side equation 1/2, you see what happens. It intersects twice. So as simple as this equation can be, this is probably the simplest equation you can get, you immediately see that there are 2 intersection points. 2 intersection points means 2 solutions right off the bat. And your pi over 6 solution, which you guessed, is right there. Now, what's happening here? So, drawing these trig functions and then the line that intersects, which is the other side, y equals a half in this case, it's a horizontal line, the number of intersections shows the number of solutions. And in that case, we know now that we are looking for two solutions. We are not looking for one solution, we're looking for two. And the question is, what is the other solution? Now, luckily, that's easy to get here, because if this is pi, by either looking at the reference angle or common sense or whatever, it has to be pi over 6 away from pi. So that solution there is 5 pi over 6. And we have x equals pi over 6 and 5 pi over 6 as a solution. So two solutions on this particular problem. Now, I will show other ways of getting this, obviously, but we need to know this one. Now, the other thing that you can use to solve this problem is the unit circle, right? So, if you draw the unit circle and you have your x and y axis on it, and then you draw the 1/2 line on it. So if this is your 0 and this is your 1/2 and this is your 1, right? You can see that it intersects here and intersects there. So here is your pi over 6. And remember that angles in trig are measured from the x-axis, positive x-axis. So there's this angle here, which is 5 pi over 6. Now, that's another way to come up with the same solution and to also know that there are two solutions. So that's already two ways, right? And now the third way of solving the same equation is to apply inverse sine on both sides. So leave some space here. You hit both sides with the inverse sine. That will kill off sine on the left. And you just need to solve now sine inverse of 1/2. Now, if you are recalling the chart that we did, right, chart of values, that's the one that you have to use now. For sine, we had 0, 30, 45, 60, and 90. And we had values for this of 0, 1/2, root 2 over 2, root 3 over 2, and 1. To read inverse sine from this chart, inverse sine is, here is the sine, here is a half, so the angle is 30, because sine of 30 degrees is 1/2, inverse sine of 1/2 is 30 degrees. It's the same numbers, it's just which way do you read the numbers, which way do you need this. So that's what we have for now. And this is only, so you only found one solution, pi over 6. Now, how do I find the second one? Again, I am using just a chart. I don't know anything about those graphs up there. This is the way 3. All the ways are, I don't want to say independent because they're all connected to each other. They all show the same thing, different way. But it's a way that is not using unit circle or a graph of sine. But it is using those quadrants all students take calculus. Because we have the problem which says sine x equals positive 1/2. So sine x is positive, because you could have had problem sine x equals negative 1/2, right? In which case you would be looking at the bottom two quadrants. So because your problem is sine x equals positive 1/2, you are looking at two positive quadrants. Now you already found your pi over 6 in the first quadrant. So that's all good. So now you know that there is another reference angle 5 over 6 on the other side, because that's the positive quadrant. And remember that the reference angle is always measured from the x-axis, right? So when you measure pi over 6 from the x-axis, you get pi, right? So second solution would be pi minus the reference angle, and you will have 5 pi over 6, which is the second solution. So this is yet another way to solve the problem. So now you have seen 3 different ways to solve the problem, and you are supposed to get 2 solutions on this one, because the easiest probably, and the one that I use the most, is this one, obviously, because it's the graph and you can just quickly see everything on it. I see that red line, y equals 1/2, which is the right-hand side of the equation, cuts twice, and I have the solution. And that's actually the fastest way to, and probably most secure way to know how many solutions you actually have. But for that, you need to be good with chapter 4 graphing of basic trig functions. So now, this is the sine x on 0 to 2 pi. You have to add this in, because we only have 2 solutions. If you had 0 to 4 pi, you'll add another 2. You'll have 4 solutions. And if you let this to go and have its wavy way to infinities, you are going to have infinitely many solutions. And those are very interesting as well. So right now, right, that first introductory problem had only 2 solutions, right? Because we were restricted from 0 to 2 pi. But what if I ask the same question, but this time I do not put the restriction, right? And you know that the domain of sine function is negative infinity to positive infinity. Well, all of a sudden your solution 0 to 2 pi is nowhere near the actual number of solutions, or how many, right? Because you just have 2, but in actual problem you have infinitely many. Now, why do we have infinitely many solutions? Well, it's the same graph. If this is going to go like this forever, and like that forever, and then you draw your 1/2 line through it, you see that you are getting infinitely many solutions, not just 2 that you were used to in this first bump, because this is where your 2 pi ends, right? So now you have infinitely many. Now, the first solution is still pi over 6, and the second solution is still 5 pi over 6. And all I need to do is to add the infinity through the period and times this n, where n is, well, you can do plus minus over here, where n is 0, 1, 2, 3, 4, and this will add infinity of solutions. So this is how you show infinite number of solutions if there is no, right? So infinite number of solutions. And it's always the first plus period times n. And you have to be careful with that, because not every period is going to be basic period, right? This is just sine x. What about sine 2x? X over 2, right? or literally anything else. So the period is not always going to be the basic period you're used to of 2 pi. And the reason why we put the n is the counter on which solution you are looking at. So my pi over 6 solution is right there. And that's when n is equal to 0. But then, when I jump over here, that's n equals to 1. And that one is pi over 6 plus 2 pi. Yeah, we just added the period to jump to the next solution. And then n equals 2, n equals 3, n equals 4. It keeps jumping to the next solution and the next solution. And those are infinity of the solutions that go off of pi over 6. They also go negative. If you pick a minus sign and 1, right, you go one period before, right there, and that's n equals, right, one period to the left, and you get n equals negative 1. And then you have negative 2, negative 3, and so on. For 5 pi over 6, that's the other ones. That's the other solution, right there. And that's also n equals to 0 for the first one. And then the second one, n equals 1. And then also minus 1, and so on. And you can actually compute them. You compute them by simply adding or subtracting the amount of, right, the period, and how many of those periods you have, depending which solution you want to get to. So the actual solutions here, if I'm going to do the pi over 6, right, and it's going to be surrounded by both sides, because the next solution adds 12 pi, so it's going to be 13 pi over 6 is the next one, plus 12 is 25 pi over 6, plus another 12 is 37 pi over 6, plus another 12 is 49 pi over 6. And that's going to go forever. And it also goes forever to the other side. Negative 11 pi over 6, take away another 12, negative 23 pi over 6, take out another. So you can see that this never ends. And it's clearly better to just do this than to actually list. I mean, first of all, you can't list infinitely many of them, right, to begin with, but you can definitely compact them in the 2n pi. So the form of the infinite solution, we don't need this thing, the form of the infinite solution is x equals solution first solution. How about that? First solution plus minus n times the period, and then n equals 0, 1, 2, 3, and goes forever. So that's the way we deal with this. So whatever you find, and then you just multiply it by the period. So let's take a look at a whole bunch of these things given to us in the textbook. 3 sine x minus 2 is equal to 5 sine x minus 1. They did not give us 0 to 2 pi, therefore we are on infinite domain. I will write this, but you need to know that when it's not mentioned, you are supposed to assume infinite domain. When it's not given to you 0 to 2 pi or 0 to pi, anything can be given. Generally it's 0 to 2 pi, but not always. So you have to be careful on the test, or not just the test, I mean, application, physics, engineering, right? it's not just, I mean, the exams are irrelevant. That should be always the least of the worries. The most important stuff is when you actually need to use this later on in your engineering courses and whatever else, that you are able to actually do it, because otherwise you're useless. All right, so how do we do this? Well, the same like basic algebra equations. You will put all of your variables on a pile, all the numbers on the pile. So we're going to subtract 5 sine x on both sides, get negative 2 sine x. Guys, it's like 3 apples minus 5 apples. That's what it is. Doesn't matter what, it's just coefficients as long as they're the same. And then you'll add 2 to both sides, so you'll have a positive 1 there. Then you're going to divide both sides by negative 2. Again, it's like basic algebra. And now you have negative 1/2. So by the same token as before, when you draw your sine function, now you have to draw negative 1/2 graph, which is below. That's negative 1/2. And because this is negative 1/2, you are going to have your pi over 6's on the other side in the lower quadrants. So if you are using the circle, right, you have your pi over 6's right there. And if you're using inverse sine, you're still using all students take calculus, you are in these two. So hopefully, I don't know if you can do this visually or not, but for me it's very easy to break this into quadrant 1, quadrant 2, quadrant 3, quadrant 4, which corresponds to quadrant 1, quadrant 2. I told you all of these are connected. There are different ways to do the same thing, but they're all connected. Quadrant 2, quadrant 3, quadrant 4. So looking at the sine graph, you see that because the bump is on the positive side, your y values are all positive, then you see that you have all and sine are positive. And then sine is negative, which there is no s in the bottom of the of the chart. So no matter which one of these you pick, it is going to be the reference angle of pi over 6 that you get to move away from the axis. So you will go pi over 6 this way, and you will go pi over 6 this way. So you are looking for the first solution, which would be pi plus pi over 6, which is 7 pi over 6. That will be your first solution. And the second solution is going to be 2 pi minus pi over 6, which is 11 pi over 6. So those are the two basic solutions that we have in our first period from 0 to 2 pi. But they want all of them, right? Because they gave us infinities. So the solution is x equals 7 pi over 6 plus minus 2n pi, because again, the period is still 2 pi for this. Next problem, we're going to change that. And then 11 pi over 6 plus minus 2n pi. And that has the solution for this. And there we have it. All of the solutions for this equation. It didn't look friendly, but when you realize that the basic algebra of moving left and right and multiplying them and dividing by number and all of that stuff that you did on basic algebra 1 problem, they all apply and they all work exactly the same way for trig functions. So let's take a look at some spicier cases when we actually get to change the period, and then see if the graph, right? That all depends on how good you are with previous stuff, because that's all about mathematics. Is all about that. If you know prerequisites, and if you didn't forget anything, didn't skip any concepts from before, you did well on all of them, then it's very easy to build up the next concept. But now, if you say I can't factor, well, you won't be able to solve some of the trigonometric equations that require factoring, right? So that's all that. Now let's take a look at some of these equations where they change the period as well. For instance, let's go with 2 cosine 4x equals negative root 3. So let's say this is the equation. Well, the first thing that we have to do is to get rid of the 2, right? So the problem is actually cosine 4x equals negative square root of 3 over 2. We also see cosine is negative. That will also help us later on to determine at least the second solution, right? So now I have cosine 4x, and they did give us 0 to 2 pi in this case. All right, so that's given as well. Now, how do I graph cosine 4x? Because I want to know how many solutions I need to have in this particular problem. All right, so we remember the form for our graphs from chapter 4, which was a cosine bx minus c plus d. And we know that this b is related to the period. So in our case, b is 4, and because b is 4, the period is equal to 2 pi over 4, which is pi over 2. So when I draw my cosine here, and I pick pi over 2 somewhere, let's say it's over here, I need to make sure that my cosine starts and ends with pi over 2. So that's it. So this is the basic knowledge, right, that we have from our previous section. And you say, oh, hold on. We need 0 to 2 pi, not 0 to pi over 2. Well, in that case, right, cut and paste this all the way out to 2 pi. So 1, 2, 3, 4. 1, 2, 3. I picked 4 of these as spacing. So that's a pi. That's a 3 pi over 2. And that's 2 pi. So I need to draw cosines in each one of these. So these are the min and max. We remember that the cosine starts on top and drops to minimum and goes back up. So there we go. The next one. And the next one. And now we get to stop because they want 0 to 2 pi. So if I cut this with my negative square root over 3 line, and you can always use half. It doesn't matter where you put the line. I mean, you can go and do a better job than that. It should be a little bit lower than a half. We count 8 solutions. We count 8 solutions here because the red line which is the right side of the equation, intersects the black line for a cosine 8 times. So we have to have 8 solutions. So in that case, right, we just need to figure out the first solution. And when you have your first and second solution, and when you have these two, then you will add the period. But in this case, period is pi over 2, right, to get the other 6 solutions.
Can I ask a question real quick?
Of course, always.
So the red line represents the equation cosine 4x equals negative.
No. Red line is the straight line, which is this. Negative square root, the black line is the cosine, the wave. I'm just going to get the decimals from the calculator.
So the red line represents negative root 3 over 2 on the y-axis.
Yes, because y equals a number is a horizontal line. So I'm just going to get the decimals for this. So it's 0.866. So the red line is y equals negative root 3 over 2, which is approximately negative 0.866.
So the solution
is intersection between the red and blue, red and black.
The solution is everywhere that negative 3 pi over 2 crosses over with the cosine graph. Right?
Negative root 3 over 2.
Yeah, that's what I meant.
So these are the 8. These are the black dots. Those are the solutions, and we're going to find the first two. We're going to find the first two solutions, and then after that we're going to find the rest. Okay. So the only reason why I draw this graph, I can't solve the problem looking at the graph, because these divisions and things, they're not precise enough, and you're not going to read the decimals well, and you can't deal with the pi and all of these kind of things. So a lot of these things you cannot solve it using this graph. But the one thing that this graph is amazing for is to get your number of solutions that you are looking for. So now you are going to solve the problem, and the problem is 4 cosine. Now there is a very sneaky trick that you can use, and I hope you will always use it, and that is, don't try to solve the problem as x equals blah blah blah. Solve the problem as whatever is in the cosine, and then later on divide by that number. So in this case, right, I have 4x is equal to, and now what is the cosine? Which cosine will produce root 3 over 2? And that is pi over 6. But let's just take a look at the solution for a second. If you look at that chart again of values that I gave you for sines, cosines, and all of those, now we're interested in a cosine: 0, 30 degrees, 45 degrees, 60 degrees, 90 degrees. The cosine has the same values as sine, but they're written backwards: 0, 1/2, root 2 over 2, root 3 over 2, and 1. So we are looking for this 4x, which is now as a unit over here, right? We're not, I mean, I could go and say, let's use the substitution, make it cosine of theta. Theta is 4x. We'll deal with that later. But we can also just say, you know what, this is just, the whole thing is an angle. And let's just keep it as a whole thing. Also, the way you can deal with it is you say cosine inverse on both sides. That's also another thing that you can do. And then cosine inverse kills the cosine, and you just get 4x equals 2. That's another way of dealing with this. So what do you have now? Well, you know that the cosine inverse of 30 is pi over 6. But that would be in the first quadrant, right? All students take calculus. It will be pi over 6 in the first quadrant. But cosine is not negative in the first quadrant. As you can see, cosine is positive in the first and the fourth quadrant. You need the pi over 6 angles away from x-axis in the second and third quadrant. Let me draw this bigger. So from the chart, we know that the answer is related to pi over 6. Now you go into all students take calculus. And you use pi over 6 angles in the quadrants where cosine is negative. Why negative? Because it was negative over here in a value. Now, what are those two angles? Well, the top angle is pi minus pi over 6. So this angle is 5 pi over 6. So 5 pi over 6 is your first angle up there. And then the second angle is 7 pi over 6. So the second is 4x equals 7 pi over 6. Because now you are adding pi over 6 to the middle, which is pi. And by the way, that's 6 pi over 6, right? So we find common denominator. So 6 pi minus pi is 5 pi, and 6 pi plus pi, 7 pi. So that's how we have those numbers. And now you just need to divide both sides by 4. Or easier, multiply by a quarter, because you have a fraction on the other side. So if we multiply both sides now by a quarter, your first angle is 5 pi over 24, and your second angle, which is the answer, is 7 pi over 24. That's the first, and that's the second. All I need to do now is to add pi over 2 3 times and add pi over 2 3 times to come up with the other 3 for each one of these. Because I got these two angles. This one is 5 pi over 24, and this one is 7 pi over 24. So now add pi over 2 to the first one, you land here. Add another pi over 2, you land there. Add another pi over 2, you land there. So you will, every time you add a period, you move the next solution in the next period. Then you start reset with 7 pi over 24, and then you will get the second set of solutions, this one, and this one. And you have, but it's important to know how many, because if you can't graph, if you can't intersect these lines, if you don't know what's going on there, you might keep going, and the problem that has 4 solutions, you list 16 solutions. Well, that's not good, right? Or the problem that has 8 solutions and you list only 2 or 4 or 3 somehow, right? So you have to be careful. It's not just what is the answer, but how many of them do we have? And this is where a lot of students, part their ways with trig and math and say, forget it. Because not paying attention to detail, or not having enough of the prerequisites, right? Not having enough knowledge from before to put all of these things together. And we use these things later on in calculus and in differential equations. We have to solve trigonometric equations all the time. So if not, you just need to survive your exam somehow, and then magically you will be good. You won't, especially when a lot of calculations later on, structural engineering, mechanical, electrical, they have a lot of trig. It's not just learning, this one little thing and you're good to go. So let's go. The next solution. The first solution was 5 pi over 24. We have to go and add pi over 2. Well, times 12 for common denominator. So 5 pi over 24 plus 12 pi over 24. You got your second solution for the first set, and that is 17 pi over 24. And as I said on the graph, that will be this one right here. So that will be 7 pi over 24. What is the next step? The next one is add another pi over 2. Now that's again times 12 and 12. So we might as well start writing just 12 pi over 24. So 17 pi plus 12 pi over 24 with a common denominator. The answer is 29 pi over 24. So that's your next solution, 29 pi over 24. And the last, fourth solution, right, is because you have 4 solutions off of the first and the 4 from the second, right? So this is the fourth value now. 24 plus 12 pi over 24. Told you I'll start skipping steps. And that's 41 pi. 41 pi over 24. Now, let's write. So x equals 41 pi over 24. And it's good to check, right, if this solution is still in the 2 pi. Well, there is another school of thought, but somehow I feel it's dangerous, especially if you're shaky with fractions. But we'll talk about that as well. 41 pi over 24. Now, 24 times 2 is 48, right? So 2 pi is actually 48 pi over 24, right? And this is 41. So that's less than 48, which means that this is in 0 to 2 pi. So that's a good solution, right? It's still within. Now, if you, by mistake, add another 12 pi over 24 to come up with yet another solution, you will get 53 pi over 24, and that's over 48 pi, so it's not in the range. I mean, domain, sorry. So that one would be discarded. Now, some people, scary, hairy, Larry, some people don't do this analysis. They just say, oh, I'll just keep adding period, and whenever I go over 2 pi, I will stop. You can still miss solutions that way. That's just, blindly going into the... I wouldn't recommend that. Graph, because you should have that solid knowledge of graphing from chapter 3. Sorry, from chapter 4. So this graph should not take less than a minute of your life. Because, I mean, if you have solid knowledge of graphing, if you're wasting your time on a calculator and trying to match things and blah, blah, you never learned it, of course you can't do it. I understand. In that case, good luck with the rest, right? But if you spend time and you did a lot of problems and you can graph these things easily, because we literally just did this. It's divided 2 pi by 4 and filled in the period boxes, right? That was it. It is very quick. All right, so that was the first set. So let's get them all. We have the first solution, the second solution, the third solution, and the fourth solution. And even if you tried another one, you got that 53 bigger than 48. So we are done with this side. Now we also have this solution, and that's going to be our first solution to give us our second set. So second set is 7 pi over 24 plus, we said 12 pi over 24. That's 19 pi over 24. So x equals 19 pi over 24. And that's our solution number 6 out of 8. Start from that solution again. Add another period, which is pi over 2, which is actually 12 pi over 24. And when you add these, you get 31 pi over 24. So x equals 31 pi over 24 is the next solution in the mix. Last solution is you start with 31 pi over 24 and you add another 12 pi over 24. That gives you 43 pi over 24. That's less than 48, which is good. And that would be our 8th and last solution for this problem. So there they are, all 8 solutions. We anticipated 8 solutions. We got 8 solutions. And then we move on with our life. I hope you will watch this if there are doubts and things. You just watch this again and see. I will always take your questions. If you have any questions, please. This is a perfect time to ask. But you can always also rewatch the video. You can do tangent problems and secant, cosecant. There's a lot of stuff. Let's take a look at problem 32 because it has a tangent in it. And you will see it's always the same procedure. It's just, can you actually do all of these calculations? Tangents x over 2 is equal to root 3 over 3. And it's on 0 to 2 pi. Good. Now, tangent period is pi, so technically it's like 2 periods, but then the period was tempered with over here because it's not x, it's x over 2. So we go b equals 1/2. For the tangent, period is equal to pi over b. That's something that, again, you need to know from chapter 4. So now, the period is pi divided by 1/2, which is actually 2 pi. So we just made the period of tangent to be the same as the sine and cosine. Okay. Now, the tangent was not shifted left or right, which means that the middle of the tangent is still going to hit 0, 0. So let's draw vertical asymptotes. And now, because our period is 2 pi, each asymptote will be at pi because it has to be centered, right? And if the whole length is 2 pi, then halves on each side, which is a single pi. And we draw the tangent function. And then when I draw root 3 divided by 3, there's only one intersection. We are expecting one solution. That's it for this particular problem. I was able to graph the tangent, and there you go, one solution. So let's see what that solution is. Again, you can use inverse tangent if that's going to help you. To get through this first part, because you are getting x over 2 is equal to, and now you need to know what inverse tangent of root 3 over 3 is. Now, you maybe know that, maybe you don't, but again, it's the same chart over and over again, so maybe one day you sit and learn it if you don't know. This is the chart with the important values, and then you get it by dividing the numbers from sine by the numbers of cosine. You get 0, root 3 over 3, 1, root 3, and undefined. So there's your root 3 over 3, again at pi over 6. How boring, right? And then you multiply both sides by 2, x equals pi over 3, And that's your solution. That's the only solution you have. Pi over 3. The graph shows that you only have one solution, so you don't have to mess around with adding the periods and or writing infinitely many solutions because they just wanted 0 to 2 pi. And how do I know that there is no other solution? Because there will be another tangent graph over here. Look, there is a distance from this end that it's below, which will start here. This end, where it starts, is a pi away from the asymptote. From the center, I mean. So, when this goes up, it will hit here at 2 pi. It will hit the axis. It's not going to be long enough to make another intersection up there. So that's why we know that there are no other solutions. Even though our graph only shows up to pi, we know that the bottom part of the tangent is going to hit up to there. Now, we don't care about this side, obviously, because it's 0 to 2 pi. It's not negative 2 pi to 2 pi to care about the solution that would happen here, right next to the asymptote. I guess no questions. So, okay. Then let's take a look at more examples. This is all about working out many of these, and once you get the hang of the fact it's always the same thing over and over and over again, we're good to go. We didn't do any secant problems, so here's 35. Secant of 3 theta over 2 is equal to negative 2. And we're still on 0 to 2 pi. Do we have problems that are not on 0 to 2 pi? 0 to 2 pi, 0 to 2 pi, 0 to 2 pi. They're all 0 to 2 pi. What? Come on, book. Yeah, it's lame. Oh, find all solutions. Problems 11 through 24. Okay. And we actually did 2 problems from that list, so. All right. So now we have a secant problem. And the secant problem is, we know secant is 1 over cosine. So anytime we need to deal with a secant in any way, we're technically dealing with a cosine. So what should I do? Well, we're going to start by doing the graph again, intersecting it with negative 2, and dealing with that way. But since secant theta is equal to 1 over cosine theta, we know that the period of secant is the same as the period of cosine, which means that the same formula P equals 2 pi over B is the formula that we get to use. And as you can see, our B is 3/2. So we have period to be 2 pi over 3/2, which is 4 pi over 3. So that's the period, 4 pi over 3. Now, when we draw, and this is a good review also for your chapter 4 graphing of trig functions, when we draw the secant and cosecant graphs, we actually draw sines and cosines and then flip them inside out. So if my period is 4 pi over 3, and the secant is connected to the cosine, I should have my cosine start, and I'm just going to put the let's say green, because this is not what we want, right? So I'm just going to put it there. And then I say, well, that's 4 pi over 3. I need to go to pi, 2 pi. So I need more. So let me add another one, which is 8 pi over 3. And then realize that that's too much. So we'll have to chop this up somewhere in between. So 8 pi over 3 is bigger than 6 pi over 3, which is 2 pi, right? So this is where I actually need to end. Right here. I need to end right there, because that is 6 pi over 3. So now I have my cosine, and what we learned in chapter 4, that for secants and cosecants, anytime when sine and cosine hit the x-axis, you get the vertical asymptote there. So we have a vertical asymptote here, we have another vertical asymptote here, and finally another asymptote there. And just now flip these outside. Now you can delete the green stuff if you want to. The red needs to stay. Red is your red are your vertical asymptotes, which are the part of secant function, and the black is obviously the secant graph. So the red can go. Sorry, red can go. Green can go. Red stays, black stays. Now, where is my, if this is my -1, my -2 is right here, and that's this side of the graph. So when I graph that one, we see that we are looking for 3 solutions. We are looking for 3 solutions. Just because the black line intersects the red line 3 times. Again, this line is y equals -2, which is the right hand of your graph, and the black line is the secant graph, which is the left side of your equation. Okay, looking for 3 solutions. That's good. So can I just deal with secant? Well, I actually don't have to. I can convert this secant into a cosine. We could have converted this function, I mean this equation, immediately and just never dealt with secant. I just wanted to show that you can do it. Secant and the graph is a joke as well, which is also a good review for chapter 4 stuff. Because, you know, just having, let's say, this much could be a question on, let's say, on exam for chapter 4. Just graph secant 3 theta over 2. And obviously, if you don't have all of the stuff that it's on the side, you clearly, right, use the calculator. You didn't graph it yourself, because you can't just come up with this without any of the side calculations. Anyway, secant 3 theta over 2 is equal to 1 over cosine 3 theta over 2. So the problem now becomes 1 over cosine 3 theta over 2 is equal to -2. And now flip both fractions. Now I'm going to say both. Yeah, both. Boom. There we go. Both. So cosine 3 theta over 2 is equal to -1/2. Easy. Right? We know exactly what to do now. We know we're looking for 3 solutions, but we already had cosine and a 1/2. Like, all of our questions are giving pi over 6. This is scary. But oh no, we didn't have the cosine of. We didn't have a cosine of 1/2. We had a cosine of √3 over 2. So cosine and a 1/2. All right, cosine 3 theta over 2 is equal to, leave some space so that you can hit this with the inverse cosine, and you're left with the 3 theta over 2 is equal to the inverse cosine of negative 1/2. Now, from that chart, right, is you know that the cosine of 1/2 works with pi over 3. So this is pi over 3. But you have to be careful, or all students take calculus, right? That's a reference angle, is pi over 3. You have your negative cosine here and there. So these are your pi over 3's. So this one is 2 pi over 3, and this one is 4 pi over 3. So 3 theta over 2 is equal to 2 pi over 3, which is the top, and then 3 theta over 2 is equal to 4 pi over 3, which is the one on the bottom. 4 pi over 3 obviously from the main x-axis, right? The first quadrant. Now, deal with your basic arithmetic here. Multiply both sides by 2/3. So first theta is 4 pi over 9. And the other theta, when you multiply by 2/3, is 8 pi over 9. We need one more. And for that, we will add the period. And we'll add the period to the smaller one, because that one is not going to run over 2 pi. And we'll add it to the other one too, just to show that we go over. So the period was 4 pi over 3. So this theta is going to be 4 pi over 9 plus 4 pi over 3 times 3 for common denominator. So that's 9, 12, 16. 16 pi over 9. There we go. So common denominator of 9, and yeah. So 9 times 2, that's 18. So 18 pi over 9 is 2 pi. You see that 16 is less than 18, so that's a good solution. Now, if you are to add to this one, 4 pi over 3 period, I'm going to erase this. You will see that you go over 2 pi. So plus, well, 12 pi over 9 is the common denominator. So you get 20 pi over 9, and that's bigger than 18. So that one would not be in the 20 pi over 9 is exactly this one, because this line would go down and that would create that solution there, close. But again, it's not in the 2 pi range, therefore it gets kicked out. And the only 3 solutions we have are the 3 solutions that you see over here. Cool. This is a dramatic pause, not just for drinking water, but hopefully a question or two. But I guess this is way too easy, so no questions, which is awesome. I mean, if this stuff is too easy, then that's great. All right, so now this would be what you would call basic equations, because we did not do any identities, we did not do any excessive algebra. Well, do you do any algebra actually at all, almost? This was just, you have the equation, you figure out how many solutions you have, You solve the equation and you're done. So that's so far. Some equations require you to first put them in the form so they are right, so you are able to solve them. And the way you do that, let's pick any of these problems, like what looks bad over here. We can do the cosine 2x, for instance. Let's see 74, how bad this gets. Or maybe it's really easy, I don't know. Cosine 2x plus cosine x plus 1 equals 0. Well, in order for us to solve the equation, we have to have a single cosine. I have two different terms with cosines, and then they don't even match, so I can't add them up on a pile. So we have to use trigonometric identities to get rid of the double angle. Now, luckily, we learned the double angle at some point, 5(2), 5(3), whatever. And we know that that's cosine squared x minus sine squared x plus cosine x plus 1 equals 0. We just made it worse because we added sine now. Okay, there is an easy fix for that, luckily. Maybe I should keep track of the basic formulas we are using on the side. Because sine squared x plus cosine squared x is equal to 1. So now I can solve this for sine. And my cosine squared x minus, this becomes 1 minus cosine squared x plus cosine x plus 1 equal to 0. Just combine like terms now. I have cosine squared x minus 1 plus cosine squared x plus cosine x plus 1 equal to 0. Cosine plus cosine squared is 2 cosine squared x plus 1 cosine x, and then these guys cancel. And now we have this equation, which we can... So what is this equivalent to? This would be equivalent like having 2x squared plus x equals 0. So if you can solve this, you should be able to solve that from algebra perspective, because that's the same question. Except it's not just the basic x, it's the cosine of x, which kind of brings us to those extra solutions and things like that. But the form of this question is the same. And if you know the trick for the one on the right, which is literally algebra 1, then you should be able to know immediately that factoring a single cosine here and then 2 cosine x plus 1 equals 0, and then using the zero product rule, saying cosine x equals to 0 and 2 cosine x plus 1 equals to 0. So that's exactly the same way you would solve this problem in algebra 1. You would factor out x, then you would set x equal to 0, 2x plus 1 equal to 0, x equals negative 1/2, and you are done. Right? That is algebra 1. Now I need you to see that this is line by line the same, because the next step over here is to write that the cosine of x is equal to negative 1/2. So we are now ready to solve, and you technically have two equations to solve. One will give you a number of solutions, the other one will give you some solutions, and then You put all of those solutions on a pile, and those are all of your solutions. Now, I think we solved cosine equal negative half somewhere. Right here, right? Yeah. Cosine equal negative half is pi over 3. Awesome. So cosine equal negative half, when you have your, well, we don't need this stuff. I'm just going to get rid of this actually, so it's not confusing. You know, if you're not paying attention, then you look it over and it's like, what is that? All students take calculus. Cosine is negative here and here, and we need those pi over 3's, which is there and there. So from here to here is pi over 3. Remember, you always get the reference angle from your basic calculation, and then you have to come up with the actual angle from this side. So you have your x equal 2 pi over 3 and 4 pi over 3. So those are the solutions that we get for this side of the equation. The other side is much easier. It's just a basic cosine equals 0. And you can there and there, right? So x equals pi over 2 and 3 pi over 2. That was like a lecture 1 on graphing, that the cosine goes through pi over 2 and 3 pi over 2 on x-axis. So there they are. We have 4 solutions for this trigonometric equation on 0 to 2 pi. I keep forgetting to put that, but they did have that in the problem as the shutoff. Now, if you need to list these as infinite solutions, just put plus 2n pi, and it will go forever. Now, let's say you care and you want to check. Well, take these solutions one by one and plug them back in the original equation. Because, guys, this is equation. If you are solving x plus 3 equals 5 and you get x equals 2, you can plug these 2 back in and have 5 equal 5. That's a concept of the equation. That's not just when you did the basic equations. That's true for differential equations in calculus 4 as well. So it's true for any equation. And let's say you want to check, I don't know, 2 pi over 3. Let's go green. Check if x equals 2 pi over 3 is a solution. Well, just plug in. That's all it is. Now let's see. We were working on problem 74. So it says, oh, green, cosine of 2 times 2 pi over 3 plus the cosine of 2 pi over 3 plus 1 should be 0. All right. So I have cosine of 4 pi over 3 plus cosine of 2 pi over 3 plus 1 is supposed to be 0. So let's see how much are these values. On the unit circle, that's again one of the ways. Here is your pi over 3. Here's your 2 pi over 3. Your 3 pi over 3 is pi. And your 4 pi over 3 is here. So all students take calculus. That's a negative and that's a negative. So cosine of pi over 3 is 1/2. which means that this one is negative 1/2, plus this one is negative 1/2, plus 1 should be 0, negative 1 plus 1 equals 0, 0 equals 0, yay. It works. So either way, you can obviously check if all of those 4 solutions, not just one, but all 4, and make sure that they all work. That's obviously just, it depends on how interested you are in these things, including the success. All right, let's do one more, and then we're going to go for the break. This way you'll have a lot of these. We can do another class, right? Next class we can do another problem or 2 for this. So we did the secant, we did sines and cosines and tangent. So how about you pick at random? So let's say anything 53 to 62. We didn't do anything from that batch. 53 to 62. Pick one. Hello? Are you guys awake?
What was the question?
To pick a number between 53 and 62.
57.
57. Cotangent x cotangent x times tangent x minus 1 equal to 0. Wow. Okay. Well, this is you can, well, if you want to graph and see the number of solutions and all of that stuff, you will take this. Oh, we are on 0 to 2 pi. I keep forgetting this stuff. All right. So you write this as cosine x over sine x times sine x over cosine x minus 1. And then when you multiply, you see that these guys cancel. So you just get 1 minus cosine x over sine x equal to 0. That is 1 minus cotangent x equals 0. So, I mean, if you know that cotangent and tangent cancel, you can just cancel them right away and go from the first row to the last row immediately. But, you're learning, so it's okay. Go to sines and cosines, and eventually, right, when you do enough of these identities, it would make sense. So now, you have cotangent x equals 1. And on 0 to 2 pi. So that happens to be where cotangent lives, but we are going to take a look. Remember that the period for cotangent, because it's not changed, it's x, right? Period for cotangent is pi. So we'll have to draw 2 cotangent graphs over here from 0 to 2 pi. And the other side is 1. So there we go. 2 solutions. So now we know that we are looking for 2 solutions. Okay, let's find. Well, the cotangent x equals 1, and you apply the inverse cotangent on both sides, you will get x equals inverse cotangent of 1, which is pi over 4, because the tangent and cotangent have the same value in the middle, right? Because cotangent is 1 over tangent, so at pi over 4 they're both 1, so that's why they share their value. I mean, the sine of 45 divided by cosine of 45 is root 2 over 2 divided by root 2 over 2, which is 1. Or cosine divided by sine at 45, it's still root 2 over 2 divided by root 2 over 2. So either way, you get 1. So we found that our first solution is pi over 4. The second solution, we know, we add the period. So that's going to be pi over 4, and the period is pi over 2 for the 3 pi over 4 total. So the second solution is 3 pi over 4. And there it is. Woohoo! 2 solutions. And yep, that's it. Any questions, concerns about these trigonometric equations? Yeah, a little bit convoluted here and there, but doable. Everything was 100% clear. Awesome. Well, in that case, bye, and I will see you in the next class.